Hello, everyone. Good morning. Dear authors and invited guests, welcome to Technical Session 10C. I am Pranjal Banage, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communications Technology for Sustainable Development, ICT4SD 2026 in Goa, India. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held the day before yesterday, 9th July 2026 in Goa, India, and the virtual event is being held through Zoom from 9th to 11th July 2026. I hope you'll enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 10 presentations. Each presenter will be given 10 minutes for their presentations and 2 minutes for question and answers. In 8 minutes, I'll raise a gentle reminder. There's another request to all the participants that you all stay connected with us till the closing remarks. If you have any queries or updates, then you can write it to me or to my co host in the chat box. Now, before we start the session, I would like to introduce you all to the chair of this session. Dr. Praveen Chopla is a professor in the Department of Electronics and Communication Engineering at Andhra University, India. He also serves as the chairman of Board of Studies, UG Electrics, at the university. His research interests lie at the intersection of signal processing, machine learning, and Bayesian estimation, with applications spanning engineering, biomedical science, and economics. Now, officially starting this session, I would like to invite the first presentator, and I'm so sorry if I mispronounce your name, Gareth Garrick. I'd like to invite you to present your paper on communication architecture influence on the manufacturing scene, a review of results on smart manufacturing units. You may start with your presentation.
Thank you so much. Can I just confirm you can hear me and
Yes, you're audible.
and you can see my screen?
Yes, we can see your screen.
Okay. Yeah, please let's start. Hi all, thank you so much for joining me in my presentation titled The Communication Architecture Influence on the Manufacturing Scene. I am your presenter from our paper of myself and my two co-authors of Professor Rengith Kuriakos and Professor Herman Vermaak from the Central University of Technology. And from my side, this is the culmination of my doctoral research, highlighting the results from my study. To start with the aim of the study summarizes the creation of the communication architecture and implementation for its intelligence actions being embedded into smart manufacturing units during production to monitor and improve production efficiency. The scope of the study evaluates the effective use of the communication architecture on a watering bottling plant case study. The water bottling plant consists of tasked smart manufacturing units tasked to fill, cap, and package water bottles to daily customer orders. The system is simulated in MATLAB Simulink and is evaluated across 4 different manufacturing scenarios to measure the adaptability and effectiveness of the communication architecture. Simulation results were measured across 1,000 runs with random environmental variability added and is summarized and averaged in this presentation. Onto some of the background literature review to speed things up for everyone to get into parts of it. The smart manufacturing units are a series of studies where information into machines is embedded through enabling technologies of Industry 4.0 with certain characteristics to bring out intelligence into the machine's processing capability. These characteristics are mentioned as interoperability, iOS, cloud manufacturing, and cybersecurity, to name a few. For architectures, the world has been filled with hardware and software architectures to govern the creation and development within their own spaces. However, communication protocols fall short of the full definition of a communication architecture by offering strict bounds of operation and no flexibility in the organization and facility of flow of information through networks nodes and describing how the interaction between them exists. This was the culmination of our study to therefore create a communication architecture on the same effective layer as hardware and software. a bit of a background into the study of this application. This study highlights and showcases some of the results of the work that was done through the creation of the architecture, where previous studies had a look at defining the need for the communication architecture and establishing some of the core ideas of the communication architecture, being with decentralization, information appropriateness, network hierarchy, and so on. On the subject of the methodology of the study, we have simulated the smart manufacturing bottling line that produces custom water bottle to customer orders. This is done by having a cloud server that handles customer orders that is scheduled and organized daily production batches based on delivery dates. A central server works to distribute the task to the additional smart manufacturing units. There are 3 stations at the production facility to fill, cap, and package a variety of orders of 300 and 500 milliliter water bottles to customer orders. The cloud to server and server to SMU communication is facilitated with an IPv4 connection, while the smart manufacturing units themselves are able to communicate with each other through a specifically designed smart manufacturing communication packet. This is called our SMP. The communication architecture facilitates, organizes, and guides communication at the server to machine and machine to machine communication levels. It does this by following specific conditions designed into the border of the hardware and software layers, either by organizing the data into specific locations and packets or dictating how the information flows from one network node to another. The communication architecture focuses on allowing the information to be appropriate at all network layers, being distributed between nodes, providing a network voting hierarchy for decisions makings during production, while offering a decentralized way for communication between machines. The organization of this information across the machines allow the machines themselves to embed contextual awareness of the network information around it by having access to information of the surrounding machines. The communication architecture does this by specifically having input into the data packets of the SMP. On the right, you can see our implementation of the specific SMP onto the MATLAB Simulink, where we developed it into a Simulink block. This block is then able to be imparted into information from a variety of network nodes, including the machines themselves and automatic software scripts that could run in the background. This is done in part in the smart manufacturing protocol designed in Simulink by dictating and organizing the information in dedicated packet areas for quick and easy access. But this access also has an intelligence level built into it directly when used correctly. Machines connected on the network are able to self-identify possible production tasks within the machine identifier flag. This allows machines to know what other machines are connected along the network and allows it to perform modularity and self-predicting tasks for the production information given. The communication architecture also dictates when updated messages should be sent and what recent data may be used in certain calculations at the application software layer. These loops and checks are handled continuously throughout the production and are entirely software-based, but are based still within the communication architecture. We have also simulated a variety of different manufacturing scenarios of customer orders of combinations of 300 and 500 and ran them through specific manufacturing scenarios of first in, first out, required delivery date organization by bottle size, and at random bottle insertion to add variability. Onto the results of the study. The study runs a baseline production benchmark on each scenario, shown in the graphs by the blue line, while the communication architecture implementation is then run and represented on the orange line. The bottle type of either 300 or 500 milliliters is shown with the red, and the long production nature of these graphs makes it a bit of a chaotic representation, but further analysis shown on the above average improvement of the total production time. When comparing the total cumulative production time and zooming into the completed bottle order numbers, clear improvements can be seen. Across each production scenario, a minimum of 10% of production efficiency improvement is seen. But this information alone does not tell us exactly what is being improved and how it's been done. analyzing the per scenario time and the patterns of the completed production set step, we can see that the machines are able to communicate to each other to be in a prepared state to receive the next bottle much earlier than the baseline architecture. This is done so it can help machines prepare and continue with production without waiting while bottles are sitting at the station idle and creating a bottleneck. Onto the graph of the baseline compared to the communication architecture, we can see that there's a correlation between the different types of scenarios of the production lines where they would come together, but this is seen as the total number of bottles that needed to be completed not changing, where each of the customer orders will have to be completed, but there would still be some variability in each day-to-day or bottle-to-bottle production, and you would see a culmination within the graph, but still an improvement with the baseline compared to the communication architecture implementation. To summarize, the study implemented an improved manufacturing response with the communication architecture through the organization and facility of flow of information. Within the machines themselves, embedded intelligence is allowed to be taken effect with complementary traits from the communication architecture and smart manufacturing characteristics. This gives greater ability to control the manufacturing setup and monitor the production efficiency. This also gives greater access to each machine for the information appropriateness, contextual awareness, distributed information and tasks, decentralized operation, and network hierarchy. The study saw at least a minimum of above 10% of improved production time, which overall was about 700 seconds, and added an additional layer of control for production events. For the future work of the study, we hope to take it into a practical real-world implementation, while also expanding into other production domains of all production manufacturing and cooperative 3D printing. We also hope in future studies to integrate this with further Industry 4.0 technologies with the inclusion of digital twins, autonomous industrial negotiation between smart manufacturing and AI agents for production metric monitoring, human-machine AI collaboration decision-making, and predictive maintenance on default tolerance and detection integration. Thank you.
Thank you so much for your insightful and valuable presentation. I'd like to ask if the session chair has any questions. I don't think that's the case. Then we'll be moving forward. I would like to invite Janushya Rajakumar to present her paper on data-driven analysis of university past papers and lecture content for curriculum optimization. You may start with your presentation.
Good morning, everyone, and myself Janusha I'm from Sri Lanka. So today I'm presenting an AI-driven learning system built optimized exam preparation for the database management system. So traditionally, university courses have a structural gap. What is written in the syllabus and what is taught in lectures and what is tested in the past papers often do not align. So this leaves students with a massive blind spots, causing them to waste energy studying less relevant topics while completing missing highly weighted exam content. So to solve this, so we have focuses on four key pillars. So which is like generating the realistic exam-aligned model papers from the lecture notes, providing summarizations and flashcards and audio revision tools, and evaluating the students' essay answers dynamically using the Bloom taxonomy. And the last one is like building a personalized MCQ study paths to fix individual knowledge gaps. So this is our overall architecture. So we inject lecture PDF and past papers into a data layer powered by MongoDB and Fire's vector storage. So our intelligent backend processes this data using RAG multi-agent frameworks, and reinforcement learning loops to deliver the personalized study materials readily to the student. So we are going to see each one of the major system that we have developed in our system. So to generate the context aware materials, we build a custom RAG pipeline. So we extracted the text from the lectures, run a hybrid search to find the most relevant material, and feed those specific facts into the LLM context window. So this completely prevents model hallucinations and ensures all short notes are strictly accurate to the professor's styles. So for our vector database, we use all many LLM model for fast, efficient, and text embeddings. So we store those like inside the files for rapid similarity lookups. So each chunk is securely tagged with a metadata pointing back to its specific lecture week and syllabus sections, and ensuring the pinpoint accuracy. So to generate the high quality model papers, we use a collaborative multi-agent loop. So a blueprint analyst enforces the formatting. A researcher pulls facts using the rack. A writer drafts the questions, and critics reviews the quality. If a question fails, it enters a localized repair loop until it meets the exam standards. So this is another type of multi-agent collaborative engines where we use agents and tools and crews for the orchestrations building. So for the tools we use RAG, and for the audio we have used the TTS tool, and to create a calendar event we use the calendar tool and the search tool to get a content from the web. So these are the multi-agent collaborative engine that we have used in our session. So for the multi-choice personalization, we use GraphRag to map out the connection between the topic concepts and MCQs. So by tracking these dependencies, the system identifies the extract prerequisite concepts a student is missing. So we combine this graph with a Bayesian knowledge tracing engine to mathematically model and update a student's mastery level over the time. So for the essay answers, we deploy a reinforcement learning feedback loop. So the system tracks the student's current mastery level as the state. So when they submit an answer, the correctness score acts as a reward. So this system then takes an action by scaling the question difficulty up or down. So ensuring the learning path dynamically adapts to their needs. So to tie everything together seamlessly, we use N10 workflow automation as our central controller. Instead of hard coding fragile script, N10 orchestrates our APIs, manages webhooks, and triggers automated background loops. So the moment student struggles with a specific topic, for the classifying text into a cognitive level, we benchmark three models. So our linear SBC model achieved the highest accuracy at 91.56 percentage. To prevent the overfitting, we performed an extensive hyperparameter grid search, so which is successfully narrowing our final validation gap to an optimal 4.83 percentage. So finally, like we evaluated our retrieval accuracy. So GraphRag significantly outperformed standard search with an 89.4 percentage context similarity score. So this result in an excellent real world user feedback scoring a 94 percentage relevance rate for our generated model exams, and an 88 percentage helpfulness rate for our automated feedback loops. So as a future enhancements, we are thought to like go for mobile integrations, and so for the current system we have developed only for the one subject, which is a database management system. So we thought to go for a multiple modules for this system. Yeah, so in conclusions, it effectively closes the gap between the university lectures and the exam performance. Yeah, thank you for your time, and happy to take any questions.
Seems there are no questions. Thank you so much for such a wonderful presentation.
Thank you.
We'll now be moving forward. I'd like to call upon Yash Mahajan to present his paper on deep learning for environmental sustainability, evaluating residual architectures for microplastic detection, classification, and segmentation. You may start with your presentation.
Okay. Is the screen visible and I'm audible?
Yes, Yash, your screen is visible and you're audible as well.
Okay. So, good morning, everyone. My name is Yash Mahajan, representing the Department of Computer Engineering, Visit Mumbai. Today, on behalf of my co-authors, I'll be presenting our research on evaluating residual architecture specifically for microplastic analysis across three different fundamental computer vision tasks. So let's briefly look at the roadmap for the next 8 minutes. We'll begin with the environmental operational motivation for this work. From there, we'll dive into our experimental design, discuss the performance and the gradient flow analysis results across the network depths, and conclude with the practical implications of deploying these models at the edge. To understand the topic, let's discuss why this application of computer vision is so critical right now. We know that microplastics, smaller particles than 5 millimeters, pose a massive threat to the global aquatic ecosystems. Sewage acts as a primary source for these particles to reach our oceans. Currently, identifying them relies on highly accurate but resource intensive lab techniques like FTIR, Raman spectroscopy, and SEM. These methods are slow, expensive, even though they are accurate, but they are confined to off-site laboratory. What the industry actually needs is a continuous on-site monitoring right at the wastewater treatment source. Deep learning offers a vast vision-based alternative, but this raises an architectural question. If we deploy these systems on resource-constrained hardware, which model backbone provides the best balance of stability, accuracy, and computational efficiency? This directly brings us to our research objective. While there are plenty of task specific models for microplastic, which may be working accurately, but I'm not going to question that. The systematic architectural comparisons on domain specific environmental data is still not available readily. Most research uses a complex model at a single task without isolating why it works. So we wanted to narrow down what our aim is. Our central question is, do residual connection consistently improve the optimization and predictive performance across segmentation, classification, and detection of microplastic analysis? And more importantly, does the performance gain justify the computational overhead on the edge devices? To answer this, we had to isolate our structure first before moving ahead. Our methodology is built on a strict controlled ablation study. We evaluated ResNet against structurally identical plane CNN at three different layers: 18, 20, and 50 convolutional layers. We completely removed the residual skip connection from the plane networks, but preserved absolutely everything else, like channel widths, kernel size, batch normalization, and stem configuration. This ensured that any difference in optimization stability, gradient flow, or accuracy could be attributed only by one thing, that is presence or absence of identity shortcut. We applied this pair architecture across three distinct data sets. To ensure our findings are generalized, we tested across three domains. For binary segmentation, we used a microplastics in sewage dataset. For classification, a freshwater sediment dataset encompassing four distinct classes like algae and fragments were used. And for object detection, a bounding box annotated dataset of microplastic scenes. Every experiment shared a standardized protocol, Adam optimizer, fixed learning rate, 30 epochs, and a fixed GPU. This rigidity is what gives our cross-task comparison its statistical weight. So let's look at the data, starting with segmentation. At the shallowest 18-layered baseline depth, ResNet variant consistently outperformed its plain CNN counterpart. We saw incremental improvements. IOU increased by 0.0036 and a die score by 0.0096. While these margins seem small, but the computational cost to achieve them is virtually zero. Training time for the ResNet increased only by 1.3% compared to the plain CNN. This proves even at shallow depths, the skip connections provide a reliable accuracy bump with negligible overhead. So what happened when we scale up the network depth? The architectural advantage becomes undeniable as we go deeper. At 18 and 20 layers, is the batch normalization is the main things which keeps the training stable. This is why our overall best performance is ResNet 20. However, when we push to 50 layers, the plane CNN begins to fragment. It completely fails to capture the fine-grained boundaries. The ResNet 50, on the other hand, yields much finer boundary. So why does plane CNN collapse while the ResNet thrives? We found the answer by looking directly at the gradient flow analysis. This perhaps is the most critical finding of the paper. We empirically tracked the L2 norm of the gradients at each layer during training, specifically analyzing the ratio between early layer and deep layer gradients. In plain CNN, we witnessed the textbook degradation problem, unstable early gradients and sharp collapsing ratio swings. The gradients simply vanish before they can update in the early features. In contrast, as we can observe, the Reset 50 acts as a gradient highway. The identity shortcuts bypass the layers during backpropagation, maintaining smooth non-zero gradient transmission, all the way back to the stem. The improved accuracy is direct mathematical consequence of this healthier gradient preservation. The mathematical advantage is not just isn't limited to just pixel level segmentation. We observed the exact same behavioral pattern for classification detection as well. The ResNet variants consistently produce tighter and more reliable bounding boxes. In classification, ResNets were noticeably better at resolving visually ambiguous samples, like distinguishing a borderline fragment morphology from algae. The benefits of residual connections are fundamentally architectural, driving robust optimization regardless of specific computer vision tasks. So how do we apply this finding in real world? To conclude, our control study confirms three things. First, ResNet consistently outperforms plain match CN across all tasks. Second, gradient tracking proves this due to stable signal transmission and mitigation of vanishing gradients. The third is cost minimal. The cost is minimal, only 1.3% training overhead at 18 layers. Practically, this means models like ResNet 18 provide optimal accuracy to compute trade-off. They're highly suitable for edge AI deployments such as NVIDIA Jetson modules installed directly at wastewater treatment sites. This opens door for continuous automated environmental monitoring as well as scalable alternative to the traditional lab workflows. Looking ahead, we aim to test our data with TinyML variants to extend this framework with more advanced and statistical validation. Thank you so much for your time, and I would also like to thank my co-authors and institution for their constant support.
As you can see, Yash, there's some questions in the chat box. If you'd please like to answer them.
Yes, ma'am. Why did you choose ResNet? Okay, so our main aim was to conduct a ablation study. We intentionally did not compare efficient net because our objective was not to identify the best architecture. It was to isolate the impact of residual connections. Efficient net changes the architectural components, whereas our study is only to compare what will happen if we do skip connection in the convolutional after every convolutional layer, and what will be the difference in the performance when there is no skip connection. That For that we observed that vanishing gradient is the main issue. And which data sets were used? Okay, if I can share my screen, I can show it. Full screen sharing is not enabled, but okay, I'll just for detection it was the MDPI dataset. For classification, we used Mendeley dataset for freshwater sediment dataset, and for segmentation, microplastic in sewage dataset, which is available on GitHub. And all these dataset are open source and free to use. What is the limitation of our work? So yes, as I mentioned that we mainly focus only on comparison of plain CNN versus the residual connection. So in some particular data set, maybe some other model like EfficientNet, MobileNet, UNet may outperform the even the ResNet. But our study is limited only to compare the residual connection and the plain CNN. Thank you so much, sir.
Thank you so much, Yash, for such an incredible presentation. I'd like to move forward by inviting Lakshmi Narayanan to present her paper on determinants of Gen Z's green clothing consumption behavior in the circular fashion economy. You may start with your presentation.
Am I audible?
Yes, Lakshmi, you're audible.
Can you see the screen?
Yes, I can see your screen.
Good morning, respected chair, reviewers, and all the participants. I'm Lakshmi Narayan from Amrita School of Business, Amritapuri. Today, on behalf of my co-authors, I'm pleased to present our research paper titled Determinants of Generation Z's Green Clothing Consumption Behavior in the Circular Fashion Economy. This study examines the key determinants influencing sustainable clothing consumption among Generation Z within the context of circular fashion economy. Now, I'll begin with the background and problem statement. So, the fashion industry has become one of the major contributors to environmental pollution due to the fast fashion model, which encourages mass production, low cost clothing, and short product life cycles. As a result, it leads to excessive textile waste, carbon emissions, and rapid depletion of natural resources. To address these challenges, the concept of the circular fashion economy promotes sustainable practices such as reuse, repair, and recycling, encouraging responsible consumption. Generation C is increasingly aware of environmental issues. However, despite this awareness, sustainable attitudes do not always translate into actual purchasing behavior. This is known as the intention behavior gap. Therefore, our study aims to understand the key determinants that influence Generation C's green clothing consumption behavior. So, research gap and objective. So, this slide highlights the key research gaps that motivated our study. First, most existing studies focus primarily on consumers' purchase intention rather than their actual green clothing consumption behavior. Second, only a limited number of studies examine how sustainable intentions are translated into real purchasing decisions. Third, previous research often investigates environmental, social, and market factors separately instead of integrating them into a single framework. To address these gaps, the objectives of our study was to identify determinants influencing Generation Z's green clothing consumption behavior within the circular fashion context. Understanding these determinants can help develop effective strategies to bridge the intention behavior gap and encourage sustainable fashion adoption among young consumers. To achieve our research objective, we adopted a quantitative research approach using a structured questionnaire and exploratory factor analysis. The questionnaire consisted of 35 items measured using a 5-point Likert scale, and the constructs were developed based on consumer culture theory and the value belief norm theory. Our target population was Generation C consumers between 18 and 27 years of age, and convenience sampling was used to collect the data. The survey was conducted through Google Forms, resulting in 262 valid responses. Finally, the collected data were analyzed using SPSS, where reliability analysis and exploratory factor analysis were performed, leading to the identification of 9 key determinants. Um, Data analysis. We assess the reliability and validity of our dataset using reliability analysis, the KMO measure of sampling adequacy, the Bartlett's test of sphericity. The Cronbach alpha's value was 0.841, indicating high internal consistency among 35 questionnaire items. The KMO value was 0.779, which confirms that the sample was adequate for factor analysis. In addition, the Bartlett's test was statistically significant with a p-value less than 0.001, indicating that variables were sufficiently correlated for exploratory factor analysis. These results confirm that our data were reliable and suitable for identifying the underlying determinants of Generation C's green clothing consumption behavior. The key findings. So, the exploratory factor analysis reduced the 35 questionnaire items into 9 meaningful determinants influencing Generation C's green clothing consumption behavior. These determinants are environmental awareness, circular clothing practices, circular fashion awareness, environmental responsibility, thrift platform value, sustainable brand trust, responsible consumption, circular fashion adoption, and social influence. Together, these 9 determinants explain the key environmental, marketplace, behavioral, and social factors that influence sustainable clothing consumption among Generation C. These findings provide a comprehensive understanding of the drivers of green clothing consumption and form the foundation for the discussion and practical implications presented in the following slides. Uh, Rather than acting independently, the 9 determinants can be grouped into 3 interconnected perspectives. First is the environmental perspective, which includes environmental awareness, environmental responsibility, and circular fashion awareness. These factors create sustainable intentions among Generation C consumers. The second is the marketplace perspective, consisting of sustainable brand trust and thrift platform value. These factors enable consumers to make sustainable purchasing decisions. Finally, the behavioral and social perspective include responsible consumption, circular clothing practices, circular fashion adoption, and social influence. These factors help convert sustainable intentions into actual behavior. Our key contribution is showing that these 3 perspectives work together to bridge the intention behavior gap, providing actionable insights for fashion brands, digital platform, and policymakers to promote sustainable fashion adoption. This slide explains the sequence through which the identified determinants influence green clothing consumption behavior. The process begins with environmental drivers, which are environmental awareness, environmental responsibility, and circular fashion awareness, which build environmental consciousness among Generation C. Next, marketplace drivers such as sustainable brand trust and thrift platform value enable consumers to make sustainable purchasing decisions. Finally, behavioral and social drivers, including responsible consumption, circular clothing practices, circular fashion adoption, and social influence, convert these intentions into actual sustainable behavior. Together, these 3 stages lead to green clothing consumption behavior and ultimately promote sustainable fashion adoption. So, to conclude, our study identified 9 determinants that significantly influence Generation C's green clothing consumption behavior. These determinants interact through environmental, marketplace, and behavioral social factors, helping to bridge the intention behavior gap and encourage sustainable fashion adoption. The findings also provide practical implications for different stakeholders. Fashion brands should build consumer trust through transparency and sustainable practices. Digital and thrift platforms should improve accessibility and educate consumers about circular fashion. Policymakers should encourage sustainable initiatives through supportive policies and awareness programs, while educators and researchers can strengthen sustainability education and continue exploring this area. Overall, sustainable fashion is a shared responsibility, and by working together, these stakeholders can help transform sustainable intentions into real behavioral change. Thank you for your time and attention.
Thank you so much, Lakshmi, for such an interesting presentation. It seems the session chair has some questions in the chat box for you. Lakshmi, are you having any issues?
Hello.
Yes, Lakshmi.
One minute.
Yeah, sure.
First question, how can fashion brands use your findings to increase circular? So fashion brands should build consumer trust, communicate their sustainability efforts transparently, and offer circular initiatives such as repair, recycling, and take back programs. Recently, H&M and such brands were using like that kind of recycling things. This helps convert consumers' environmental intentions into actual sustainable behavior. Then, how did you determine that 262 responses were sufficient? So, we used exploratory factor analysis for which the sample size were adequate. Before the analysis, we went for exploratory factor analysis. So, we wanted to make sure that the sample size was adequate and the KMO value was 0.779, indicating adequate sampling adequacy. And Bartlett's test was also significant, confirming that the data were suitable for factor analysis. Therefore, 262 valid responses were sufficient for our analysis. Um, any more questions?
Thank you so much. Now we'll be moving forward. I'd like to call upon Anusha to present her paper on GRU-based wireless link quality prediction using LiDAR empirical data in B21 outdoor environments. You may start with your presentation.
Good morning, everyone. Am I audible?
Yes, Anusha, you're audible.
Yeah, good morning, everyone. I am Anusha Antagiri from Department of Communication Engineering, CBIT Hyderabad. Today, I'll present my work title GRU-based wireless link quality prediction using LiDAR empirical data in V2I outdoor environments. This work focuses on predicting future Wi-Fi RSSI using LiDAR-based environmental sensing and deep learning. The aim of this work is to develop an environment aware wireless signal prediction framework for V2I communication. We integrated LiDAR sensing with real time Wi Fi RSSI measurements and use a GRU model to predict future RSSI values. This enables proactive wireless communication in dynamic environments. My objectives are to develop a LiDAR assistant multimodal framework in vehicle to infrastructure communication and to synchronize LiDAR point cloud features and RSSI measurements, and then to design and implement a GRU based deep learning model for multi step like future RSSI prediction, and then to compare the proposed GRU model with the baseline models like feed forward neural networks and the random forest to demonstrate the effectiveness, and to evaluate the proposed framework using threshold based accuracy and mean absolute error, RMSE, and CDF analysis. This figure illustrates the overall system architecture. A Rabin W1G LiDAR, which is a type of LiDAR, and a Wi Fi access point are placed at the infrastructure node, and a Jetson based rover acts as the vehicle node and continuously logs RSSI values at 10 Hz. LiDAR captures environmental information at 10 frames per second. Both data are synchronized to generate a multimodal dataset which is used to train the GRU model for future RSSI prediction. Finally, prediction performance is evaluated using the threshold-based accuracy. Our experimental setup consists of three main components. First one is the Robin W1 LiDAR, provides a higher resolution 3D point cloud with a 120 into 70 field of view, and then a laptop function as the Wi-Fi access point, and then NVIDIA Jetson Orinano mounted on a rover serves as the vehicle side user equipment, which collects the RSSI measurements during the movement. The LiDAR captures the surrounding environment in real time, and the Jetson acts as the mobile connected to the Wi-Fi access point. This slide summarizes the complete methodology. First, LiDAR, point cloud, and RSSI measures are collected, and then next, LiDAR pre-processing is performed using field of view filtering and static cluster removal, and then geometric features are extracted and synchronized with RSSI measurements using a timestamps. Then constructed temporal sequences split the dataset into training and testing sets. Then finally, JRU and feed forward neural network and random forest models are trained and evaluated using a threshold based accuracy. This picture shows that a real world outdoor experimental setup. The LiDAR and Wi-Fi access point are fixed at the roadside infrastructure, while the Jetson mounted rover move within the communication range. This this video shows the outdoor LiDAR point cloud captured during the data collection. It demonstrates the spatial information available for environmental sensing. We collected both LiDAR and Wi-Fi measurements simultaneously. For the LiDAR, the XYZ coordinates define the 3D point cloud, and frames are captured at 10 frames per second. And for Wi-Fi, RSSI is sampled at 10 Hz. To maintain continuous wireless communication, a 100 MB file was continuously transferred between the access point and the Jetson client. This ensures stable traffic and continuous RSSI updates during the data collection. Raw LiDAR point clouds cannot be directly used because they are irregular and higher dimensional. So we compute the range angle orientation of each point to obtain geometrical features. Then the pre-processing includes field of view filtering and angle sorting. Then the pre-processing includes field of view filtering, then angle sorting, angle quantization into 800 bits, distance quantization, and the static cluster removal and feature selection. Finally, each LiDAR frame is converted into a 800 dimensional feature vector. Each synchronized sample contains a timestamp. The LiDAR frame and the preprocessor LiDAR frame and the corresponding RSSI measurements, this form the multimodal dataset used for training. And then we use a sliding window approach to capture temporal dependencies corresponding to RSSI values. The model predicts the RSSI for next 3 time steps. We use the prediction horizon as a 3. To validate the proposed GRU model, we compare it with baseline models like feed-forward neural network and the random forest. The feed-forward neural network flattens the temporal sequence into a single vector and therefore cannot capture temporal dependencies. And also the RF model is a classical ensemble learning algorithm that also operates on a flattened inputs. These all models use the same train and test split evaluation metrics for fair comparison. In the proposed model, each time step contains an 800 dimensional LiDAR feature vector and one RSSA value, resulting in an 801 dimensional input. This input is projected into a 128D embedding and then processed through the GRU layer, and then final hidden state is passed through a fully connected layer to predict the next three RSSA values. The GRU uses update and reset gates to selectively retain or discard information from previous time steps. This enables the model to learn temporal variations in the wireless channel more effectively than non-recurrent models like FFNN and RF. We train the network using mean square error loss and Adam optimizer for 50 epochs. And the results section, the GRU converges rapidly around epoch 12 and remains stable afterwards. The final model achieves a validation loss of 0.0002 and MAE of 0.245 dBm and RMSE of 0.432 dBm at the strict plus or minus 1 dBm threshold. The model achieves over 92% accuracy across all prediction origins. At plus or minus 3 and plus or minus 5 dBm, it reaches 100% accuracy, demonstrating that reliable RSSA prediction.
I'm so sorry to interrupt, Anusha, but I'd request you to conclude your statement.
Hello?
Yes, Anusha, I would request you to conclude your presentation as your time is up.
Yeah. In conclusion, we proposed a LiDAR assisted GRU framework for future RSSA prediction in outdoor V2 vehicle to infrastructure communication. The model achieved higher prediction accuracy and demonstrated the effectiveness of multimodal learning. In future work, we plan to evaluate the framework in a higher mobility like 5G or 6G environments using additional sensors. Thank you.
Thank you so much, Anusha, for your informative presentation. There's a message from the session chair in the chat box, a review for your presentation, it seems.
Thank you, sir. Thank you so much.
Now, we'd like to move forward. I would like to invite Shivam Kumar Tiwari to present his paper on hybrid attention-based model for lung disease classification and mass segmentation from chest X-rays. Sir, you may start with your presentation.
Is my screen?
Yes, sir, we can see your screen.
So, good morning, everyone. I am Shivam Kumar, and today I will present our research titled as Hybrid Attention-Based Model for Lung Disease Classification and Mask Segmentation from Chest X-ray. The objective of our work is to develop an intelligent deep learning system that is capable of performing two important tasks at the same time, which is classifying the chest X-rays and as well as segmenting the infected lung regions to assist the radiologist in diagnosis. So this is our table of content. So respiratory diseases remains one of the major causes of the death worldwide. Traditional diagnosis depends on the radiologist manually interpreting the chest X-rays, which is time-consuming, subjective, as well as error-prone due to heavy workload. In this research, we propose an improved ResNet unit multitask network capable of lung segmentation as well as disease classification. Our model achieved a 95.32% of classification accuracy, as well as approximately 95% of precision recall and F1 score. So, lung disease such as COVID-19, viral pneumonia, and bacterial pneumonia continue to affect millions of people worldwide. Manual diagnosis has several limitations. So, we propose an artificial intelligence based model that can address these issues by learning the complex image features automatically. So we reviewed several research papers based on CNN models, ResNet 50, Efficient Net, and HOG plus SVM. Although these methods achieved reasonable classification accuracy, but they have several limitations such as no infection localization, poor segmentation quality, high computational cost, and limited explainability. So our problem statement is that diagnosing the lung infection using chest X-rays remained difficult because of chest X-rays overlapping anatomical structures and infection boundaries are often unclear. So therefore, an automated system capable of identifying both the infection regions as well as classifying the disease is needed. So our objective is to develop an automated deep learning framework capable of both lung segmentation as well as disease classification. So next slide will be of our methodology. Our methodology follows a structured deep learning pipeline consisting of several stages. Our first stage is of dataset collection. We used the COVID-Q data chest X-ray dataset, which consists of three types of images: COVID-19, non-COVID, and healthy patients chest X-rays, as well as segmentation mask, which indicates the infected lung region. The next step is the image pre-processing, where we resize all the images and normalize the pixel values. We use the ResNet 34 as the encoder, which extract the deep and meaningful features from chest X-rays while avoiding the vanishing gradient. Then we extracted features are passed on to a transformer block, which is connected with an attention gates, which only allows the meaningful features to pass from that layer. So next, the extracted features are passed on to a unit decoder. The decoder reconstructs the spatial information and predicts the infected region using the skip connection between the encoder and decoder layer. A classification head is attached to the encoder. Using the extracted feature, it predicts whether the image belongs to COVID-19, non-COVID, or normal. The model is trained using the cross entropy loss and dice loss for segmentation. So dice loss is basically a mix of binary cross entropy loss and dice. Finally, the trained model is tested using unseen images and evaluated uses standard classification, evaluation, and segmentation metrics. So this was the dataset used, which is based out of Kaggle, which contains around 32,000 images. To measure the effectiveness of our proposed model, we used several performance metrics, which were accuracy, precision, recall, and F1 score for classification, and DICE and IOU for the segmentation part. After training the model, we evaluated the performance on the test dataset. The proposed ResNet unit architecture showed 95.32% of accuracy, 95% of precision recall and F1 score, and 97.40 of lung dice, and 95.05% of lung IOU. So this graph illustrates the learning behavior of the proposed deep learning model during the training. This shows that the training increases steadily with each epoch, indicating that the model is learning useful features from the dataset, while the validation curve follows a similar trend and remains close to the training curve. This suggests that the model generalizes well and does not suffer from significant overfitting. So in this research, we developed a ResNet 34 unit-based multitask deep learning framework for automated lung disease diagnosis. Experimental results demonstrate that the model achieves high classification accuracy along with precise localization of infected lung regions. The model achieved an overall accuracy of 95.32%. Our future improvements include tuberculosis, means extending the diagnosis to several more diseases such as tuberculosis and COPD, integrating multimodal data and increasing the data set for this model. So, thank you.
Thank you so much for your presentation. It seems the session chair has no questions, so we'll be moving forward.
Thank you.
Next, I would like to call Mohammad Imrat Sargiro to present his paper on hybrid behavior-based and privacy-preserving framework with synthetic data generation for efficient zero-day malware detection. You may start with your presentation.
Hey, hi, good morning, everyone. Yeah, just let me share my screen. Hey, hi, good morning, everyone. Today I am going to present an based algorithm for privacy prevention as well as zero-day malware detection. This is part of my research, this one. Yeah, let me just go to the introduction. Right. In today's world, right, there are because of the increased number of digital devices, right, there is an increase in the landscape of the number of attacks and vulnerabilities where these devices get exposed to. So, so there is a need for so there is a need for coming up with a hybrid framework to detect these kind of threats and vulnerabilities. Right? What are the limitations of the traditional intrusion detection system? Traditional intrusion detection systems, right? They rely on signature based as well as static and dynamic uh, dynamic signatures to evaluate the threats, which struggles with this which struggles with the zero-day malware detections in these cases. Whereas if we go with the challenge with the deep learning algorithm is, even though the accuracy is high, but the deep learning algorithms suffer from high cost and yeah and hidden real time use in the edge because of their cost and the computational cost involved in the deep learning algorithms, right? So there is a need for coming up with a unified framework to detect these kind of malware attacks. Yeah, coming to the problem statement, right? Coming to the this one malware, right? There is a class imbalance. There is a huge class imbalance in case of malware detection methods. So there is an so we have to develop a synthetic data limitation, like oversampling techniques create synthetic samples that may not reflect the real malware behavior. Right, privacy versus detection conflict. If we increase the privacy, right, using the encryption algorithm, the detection accuracy will get reduced because of this. And also there are challenges with the deployment and the efficiency issues. Deep learning methods are computationally very intensive and unrealistic for the real-time edge deployments. So this is the problem statement. Uh, yeah, coming to the research gap, right? There are challenges in the malware detection. The current malware learning systems, right, struggle to detect the zero-day and malware because of the new evolving threats every day. Generalized limitations. Existing solutions often fail to generalize to new and unseen ransomware attacks, evolving threats in threat environments. Privacy versus accuracy. That's what a stronger privacy and precision often reduces the detection accuracy in the current models. Computational cost, advanced AI models impose high computational costs and limit the real-time edge deployment. So what are the objectives? The objective is to come up with a hybrid framework for this malware detection so that it can efficiently and accurately detect the zero-day malware behaviors. Right? Feature engineering pipeline is to design and develop a pipeline extracting the static, dynamic, and system calls through the network traffic. Right. Also, one of the objective is to come up with a synthetic dataset generator which can mimic the real-time threats. Hybrid detection technique. The hybrid, here we are following an hybrid detection technique wherein we are making use of supervised as well as unsupervised learning for the zero-day malware detection. Right. The work carried out is first we have developed a synthetic dataset generator which combines a lot which combines the various malware features including various class imbalance malware families and zero-day samples. Next is feature extraction technique, wherein applied static and dynamic behavioral feature extraction to accurately capture the malware characteristics. Next, coming to the framework, we have used supervised and unsupervised learning algorithms to evaluate the performance of this detection framework. Right? Performance evaluation is based on the values of precision, recall, false positive, right, and the optimized to the lightweight real-time edge deployment. Yeah, this is the different features that we have included in our synthetic dataset generator, which includes number of you can these are configurable values wherein you can specify the number of samples, the features that you want to include, malware families, imbalance ratio, nonlinear strength, and zero-day families. Yeah, the feature depicts like what is how much how we are classifying the normal traffic as well as the attack traffic. Yeah, this is the experimental setup that for the hybrid framework, right? Initially, we are starting with a data set generator. Then this data set is prepared. We do a pre-processing on it. That is cleaning of the data, handling missing values, feature scaling, and normalization of the data. Then the next step is we are using an unsupervised learning algorithm. It is isolation forest in this case, wherein the data is trained only on the beneath traffic, where we will try to identify the anomalies based on their behavior. Any deviation from the normal behavior will be classified as an anomaly, and an anomaly score will be assigned for that data set. Right. Next, after the anomaly scoring, right. Next, we move on to the feature augmentation, wherein we use the original data set along with the anomaly scores and use it as an input to the supervised learning algorithm, which is the random forest in this case. The random forest is used to classify the data properly, even imbalanced data set, to detect the vulnerabilities using the precision, recall, and false positive rate. Finally, we are validating this model using cross validation strategy. Right? Yeah, these are the results that are obtained using this hybrid algorithm, uh, wherein first we are using the labeled data. The first picture is the labeled distribution, wherein you can see that the traffic is clearly classified into the normal as well as normal and attack traffic. Next is the confusion matrix. Wherein we are evaluating the precision, recall, and F1 scores for this model. And coming to the ROC curve, the value closer to 1 indicates that the better separation between the normal and the attack traffic. Coming to the anomaly score distribution, the blue ones are the normal traffic and the red ones are the attack traffic. The more separated these anomaly scores are, the better separation is being achieved. Right? Yeah. Next, coming to the prediction probability, the model was able to predict up to 90% of the attack traffic. Yeah. To conclude, right? Yeah, this hybrid detection framework, right, combines behavioral as well as privacy preserving methods for zero-day malware detection. It handles the unseen attacks, utilizes synthetic data as a wide data set input for the algorithm for the mixed learning techniques to address the class imbalance and unknown threats. The model is very lightweight and it can be efficiently deployed in the real world environment. The feature enhancement is we want to train this with the various real world data sets and improve the privacy measuring and the optimize the large scale performance.
Thank you so much, Imran, for your valuable presentation.
Hey, thanks everyone.
Are there any questions from the session chair? Since there are no questions, we'll be moving forward. I'd like to invite Sunita Ratnakaram to present her paper on intellectual property challenges in AI-generated works and software. Ma'am, you may start presentation.
Just give me a moment. I'm opening. Is the screen visible? Can you please confirm?
Yes, ma'am, your screen is visible.
Thank you, Pranjal. Good morning, all. Right. Most of the presentations that we have heard thus far are some of the real great empirical work. I've enjoyed listening to them all. So I am Sunita, Professor Sunita Ratnakaram from UP Jindal Global University. This is a conceptual paper we tried to put together, me and my co-author, Dr. Venkam Raju Chakravaram. What we have tried is we are living in the age of artificial intelligence, and there are so many challenges when it comes to the intellectual property. There are days where we start, like our day starts something like generate a picture, use like I have this is my text, add some of the maybe the current examples, or maybe I do want to ask relevant pictures, relevant case studies. So there is most of the times some of the profs also do use it as hybrid. Some of us probably might use AI standalone, and it's doing so many works. It generates pictures, it writes codes for you, it creates movies for you, it does a lot. So, and now we have a question: who owns the creation when there's no human creator involved at all, and there's a human creator involved? Maybe it's few of the stages. Though we have not reached the stage where we can do the empirical work by having so many, creating that kind of a randomized design. Right now, what we're trying to do is comparative look at what WIPO says, WTO says, and TRIPS. This is the international bodies that are working in the arena, and how are they handling the situation. That's what we're trying to see in this paper. Now, as I've already said, and as of all of us know, a machine writes a novel, composes a song, and writes a code. So, like, who owns it ultimately? Now, that's the question this paper is trying to kind of answer. I won't say kind of answer. We attempt to propose a model wherein we will try to see more granularly. Global IP law, copyright, space, patents, the whole system was built on an assumption for over a century that a human being does everything to do with creation. AI of the day that quietly breaks that assumption, and the world's like really leading systems are trying to figure out how do we respond to this challenge. It's not one way that people are handling it. As you can see here, 150-year-old rule book, there's a Berne Convention, there's a Paris Convention, where we know that only human being is capable of creating something like maybe a text, maybe music, maybe design an image, maybe to generate some software, for that matter, even conduct research. But then, those were the times where WIPO, WTO, TRIPS, they kind of had protected all the intellectual property rights with a number of conventions and the acts. Now let's see what these institutions and what they do, what kind of job they deliver. WIPO, World Intellectual Property Organization, it just runs the global conversation. However, it cannot enforce anything. It's not, they kind of initiate conversation, they provide guidance and do come up with discussion papers, which they have already done in this particular, as early as in 2019 onwards, this conversation started by WIPO. And WTO, we all know, oversees global trade rules, and TRIPS is the most important body, which is kind of a binding rule book on all of us related to intellectual property rights. However, again, TRIPS as on day has considered only human creation, and every regulation is created around that. Coming to this question, let's just see. We try to see the comparative, between US, UK, and India. There are different other countries taking it in different kind of ways. India majorly is what's the standpoint of Asia Pacific that's coming from India. United States is super strict on this particular part, where new human and this if you don't have human involvement, there's no copyright. It's as simple as that. When it comes to United Kingdom, they kind of grant authorship to whoever arranged for the AI to produce the work. So that's the kind of a fix that United Kingdom has come up with. India is still figuring out. They have stayed cautious, like always. So most of the Asian Pacific is something like this. So we have a case of Zarya of the Dawn. I won't say this is the only case, but this is one prominent case that has been kind of recognized as the case which has really worked through this intellectual property rights and who gets what. Who gets. So here a human writer has, he wrote the story. However, artwork is generated by AI tool Midjourney. So copyright of the written part is protected by the US court, but artwork has been given like, okay, there's no copyright for this. What this said during that part is like copyright law protects fruits of human creativity and not machine generation. That's the like a very clear statement that the court chose to give. So now when this is a situation, like, why are we bothered if if AI gets to have intellectual property rights or not? Now, to answer that question, maybe before I go there, let me just bring in everybody, any business organization would want to put in a lot of effort, or maybe there is a huge billions of investment that gets into these AI machines. They would want to do it as long as they can protect the intellectual property rights to that. Otherwise, they won't be super interested and excited. The other part here is why AI, like why quotes are why the system doesn't want to give AI like this intellectual property rights on the go, because as we all know, there's huge like uh, amounts of training data that AI uses probably is copyrighted by somebody else, some other entity. So, like, there is no complete transparency when it comes to the training data, though there were certain kind of acts and regulations. So it's kind of hazy. Now, given that, there are people who are kind of not really keen on giving intellectual property rights to the AI machines who doesn't have transparent training data reveal. So now there's a spectrum of possible answers in this particular scenario. Anthropocentric, no human, no protection. This is what is going to kind of say like businesses doesn't want to invest anymore. And then when we're going to go for this particular AI autonomous, machines could hold every right, this becomes a problem for those institutions who have prior copyrights. Now, to like when we have to navigate through this kind of route, probably we might have to think of something called as co-authorship. That's what this particular paper is trying to propose. Generated work does give what's the human contribution, what's the shared attribution, like how much of human oversight was there, how much you will have to have the transparency and disclosure, then the kind of legal certainty. These are going to be the outcomes: human oversight, transparency, disclosure, maybe the global harmonization of between like different laws. Like today we're living in a global world where you can't have a law that is gone in US and very completely different in UK, completely different in China, say, than Japan. That's going to make the things really difficult or conflicting in the world. So you will have to have like a harmonized kind of law in this particular area. And so because of that reason, what we propose is have human contribution, shared attribution, and have transparency between like in the algorithms, what exactly you're doing, and ethical accountability must be there on the human as well as the AI. That's when you're going to create like maybe a system wherein you can have innovation and public interest, taking them into account. These are the gaps what we try to address: shared definition or disclosure. Finally, what's that the paper is recommending? Draft WIPO probably will have to come up with a global AI IP protocol, which is non-binding. Of course, whatever comes from World Intellectual Property Organization is non-binding. However, the guidance is something like everybody is going to take forward, and they kind of try to work. So
I'm
they
sorry to
add
interrupt, ma'am, but I'd request you to conclude your presentation.
Yeah, thank you. Like I'm done. Add AI language into the trips and form a WIPO or WTO joint task force. That's one recommendation. And finally, required, like, in everything that you do, have disclosure and transparency. Three goals the paper says: any reform must balance reward innovation, protect the public, and ensure that the global equity is ensured. So that's all we have as far as our presentation is considered. The law will decide who or what gets to be called a creator. So this is what I have. Thank you.
Thank you so much, ma'am, for such an incredible presentation.
Thank you.
It seems the session chair has no questions for you. Then
Thank
we'll
you.
move forward. And I'd like to call upon Bhuvan Kumar Patri to present his paper on optimization-driven multi-class brain tumor classification using efficient net B0 and Aquila Optimizer. You may start with your presentation.
Am I audible, ma'am?
Yes, Bhuvan, you're
Hello.
audible.
Good morning, everyone. I am Bhuvan Kumar Epatri from the Department of Information Science and Engineering, Nita Meenakshi Institute of Technology, Bengaluru. Today, I will present our work titled Optimization Driven Multi-Class Brain Tumor Classification using Efficient B-Naught and Aquila Optimizer. Basically, in this work, we combine a lightweight deep learning model with an intelligent optimization algorithm to improve brain tumor classification from MRI images. Now, coming to the problem statement and motivation, brain tumors are serious medical conditions where early and accurate diagnosis is very important. So, MRI is preferred because it gives clear images of brain tissues without any invasive procedure. However, manually analyzing MRI scans takes time and depends on the experience of radiologists. So, our goal is to help radiologists by providing faster, more consistent, and reliable brain tumor classification using AI. Coming to literature survey, as shown in the table, previous studies using CNNs and EfficientNet have achieved accuracies ranging from 96% to 99%. However, most of these methods still rely on manual hyperparameter tuning, and some models are computationally expensive. So, this creates the need for an efficient model with automated optimization. As I said, the main research gap is manual hyperparameter tuning, which is time consuming and may not always produce the best results. So our solution combines efficient net B0 with the Aquila optimizer, which automatically finds the best learning rate, dropout, and batch size, which are hyperparameters. This reduces manual effort and improves model efficiency and reproducibility. Our framework begins with MRI image preprocessing. The images are then passed to efficient net B0 architecture for efficient feature extraction. Next, the Aquila optimizer automatically finds the best hyperparameters for training. Finally, the optimized model performs classification and its performance is evaluated using different metrics. Coming to our methodology, as I said, it uses efficient B0 with the Aquila optimizer. We selected efficient B0 because it provides high accuracy while using fewer parameters than many larger CNN models. We also used transfer learning, so the model could quickly adapt to MRI images. Then the Aquila optimizer used to optimize the learning rate, dropout, and batch size, improving performance while reducing the overfitting. Coming to the experimental setup, the MRI images were resized to 224 cross 224 pixels, normalized and augmented before training. Our dataset, we chose publicly available MRI dataset, which contains 7,023 MRI images divided into training, validation, and testing sets. We used AdamW as the optimizer after introducing Aquila optimizer and cross entropy loss for multi-class classification. For learning rate scheduling, we used cosine annealing and we applied early stopping with patients set to 5 epochs to avoid unnecessary training. The model was trained for maximum of 20 epochs using mixed precision or AMP on dual Tesla T4 GPUs. Finally, we evaluated the model using accuracy, ROC AUC curve, MCC, and MAP. Here we can see the AO optimized hyperparameters. It selected a learning rate of 0.000343, a dropout rate of 0.185, and a batch size of 16. During the optimization process, the best validation accuracy improved from 97.20% to 97.99% in the Aquila optimizer phase itself. We then used these optimized hyperparameters for the final model training. As you can see, the model converges smoothly with the best validation performance achieved at epoch 13, while the training and validation curves remain closely aligned, indicating minimal overfitting. Our final model achieved test accuracy of 99.47% with only 7 misclassifications. With Matthews correlation coefficient MCC of 0.9929 and an mean average precision MAP of 0.999, demonstrating strong prediction reliability and class separation. All 4 classes achieved high precision, recall, and F1 score. A key highlight is that the no tumor class achieved 100% recall rate, meaning none of the healthy cases were missed during the testing. As shown in the table, the class-wise results also show strong macro and weighted averages, both around 0.994, confirming balanced performance across all classes. Overall, these results show strong class separability, stable convergence, and minimal overfitting. To conclude my presentation, combining efficient B0 with Aquila Optimizer resulted in an efficient and highly accurate brain tumor classification framework. The model reduces manual hyperparameter tuning while achieving 99.47% test classification accuracy. The high MCC value also supports reliable and balanced classification. In the future, we plan to validate the model using multi-center MRI datasets, extend it to 3D volumetric analysis, and evaluate it in real clinical environments. These are the key references supporting our work. Finally, thank you for your time and attention. I would be happy to answer any questions.
Thank you so much, Bhuvan Kumar, for the effort that you put into presenting this presentation. And it seems like the session chair does not have any questions for you.
Thank you.
We'll be
Thank you, sir.
moving forward then. Next, I would like to invite Gitika Alapati to present her paper on robust Telugu grocery identification from speech using perceptual feature and machine learning clusters. You may start with your presentation.
Good morning, ma'am. Is my screen visible?
Yes, Gitika, your screen is visible.
Good morning, everyone. I'm Geetka Alapati, and I'm honored to present on behalf of my team. And while coming to my teammates, Dr. Professor Ravati is my guide who constantly supported us throughout the project. And while coming to my teammate Ritika, she is the one who worked along with me throughout the project. While coming to title of my paper, The Robust Telugu Grocery Identification from Speech Using Perceptual Feature and Machine Learning Clusters. These are the contents which I included throughout the PPT. And while coming to the problem statement, why choosing Telugu language is the main reason because Telugu language is having very few data sets and it is having more complex phonetics. While coming to the Telugu states, they are having different regions in which they are having different essence. So we are choosing Telugu language is the main for this project. And while coming to the approach and methodology, we are developing a speaker independent Telugu grocery speech database. Here we have created our own database and we have deployed two methods to find out which method is having more accuracy and which can give more efficiency. And while coming to database creation, we have created our own database by recording voice samples from both male and female of age 20 to 22 years old. And we have created a data set of 10 grocery items. Each grocery item has 10 different speakers. And we have standardized the database to 16 kilohertz sampling rate according to the Nyquist theorem, which can cover a speech of 8 kilohertz and 16-bit resolution and mono channel. These are the flow diagrams of the methods we have used. Feature extraction technique using raster PLP is the method we used for both. This is the common feature extraction we have used for the both methods. While coming to this, feature extraction is the process in which like important information is taken from the speech, like extraction. And while coming to the block diagrams, here we are inputting the signal, and preempsis is the process in which boosting the high frequency components. Framing is the process in which the speech components are divided into short frames, like 10, like short duration frames like 25 ms with overlap of 10 ms. While coming to windowing, we have used Hamming window to reduce the sharp edges so that there won't be any distortions during the frequency analysis. And while coming to bar filter bank, here we are using a filter on bar scale, on which mimics like a human auditory system. Well, coming to log compression, here like how human ears perceive loudness, we are coming to learn through log compression. While coming to raster filtering, here we are using a band filter, which allows all the frequencies, but there it is reducing the slow variations and very fast noise variations. And at last, at raster PLP features, we are getting the robust features. While coming to the training process with raster PLP and GMM, here in raster PLP, we are getting features extraction as output. Here we are dividing the features into 80 and 20%. 80% are used for testing, training, and 20% are used for testing. While coming to data modeling, we are using GMM, Gaussian mixture modeling. Data modeling is required. Data modeling is required because speech signal is too complex to be modeled by a single signal distribution. So we are using data GMM because it models in a probability distribution, so that each signal is modeled according to the GMM distribution. It is having mixtures of 16, 32, and 64. While coming to the testing, we have used 20% of the features for testing. Here we are using maximum likelihood classifier, which checks the GMM maximum values and tests the features and makes a confusion matrix out of it. While coming to the second method, we have used raster PLP along with k-means clustering process. In this, instead of modeling, we are using k-means clustering. In this process, we are assigning k clusters. From that trained features, we are taking some k random values as centroids. From that features, we have calculated distance from each centroid to the trained feature, and maximum value of the features are taken as the centroids. While coming to the testing process, here from the testing features, we have calculated the distance to the trained centroids. The minimum distance, like Euclidean distance, the minimum distance which is shown, for that we are naming, we are naming the grocery name. This is the outputs of confusion matrix
for 64 Gaussian mixture because it is giving the 99% more accuracy compared to other 16 and 32 mixtures. And for confusion k-means clustering, we are getting 100% accuracy because our database is comparatively low because we are having only 10 grocery items and 70 speakers. If we are increasing the data set with more users and speakers, the accuracy may decrease. And while coming to the conclusion, we have developed a speaker independent Telugu grocery speech recognition system, and we got accuracy for one Rashtra BLP and GMM 97 accuracy, 99% accuracy, and while coming to K-means clustering, we got 100% accuracy. And for the future work, we are thinking to increase the number of speakers and check the accuracy. And while coming to its applications, it can be mostly used for grocery apps because a speaker can speak in their native language and it can be identified, and it helps in malls, marts, and other places too. And these are the references we have followed and used during the our project. Thank you.
Thank you so much, Gitika, for such an interesting presentation. It seems the session chair has no questions. Then we'll be moving forward. I would like to invite Rajesh Gudapati to present his paper on an AI-driven neurospecific extension of USDM for standardizing inclusion and exclusion criteria in Alzheimer's clinical trials. You may start with your presentation.
Yeah, Pranjal, I just joined. I'm having little internet issues. Can I do it in some time? Can you give me another 15 minutes?
So, roughly how much time would you need?
I just need the 15 minutes.
So, you are the last candidate of this session.
Okay. Maybe next session.
Just give me a minute, I'll confirm. So you can join in the next session, which will be starting at 12:30.
Thank you so much.
Yes. Then now I would like to conclude this session by sincerely thanking all of our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough, and on behalf of the whole team, thank you for the support during this 11th version and all the 10 previous versions of the conference. We'll be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICT4SD 2026. I would also like to thank our session chair by displaying this, a token of appreciation from our side on behalf of the team of ICT4SD 2026 and Global Knowledge Research Foundation and partners. I extend my great gratitude to the session chair for chairing this session with such a good energy and for his guidance throughout. Thank you everyone for your valuable presentation. Now I request you all to turn on your cameras for a quick snapshot of this virtual conference. I'd request everyone to turn on your cameras. Okay. Everyone smile, please. Just a minute. Okay. Thank you so much, everyone. Stay safe, stay healthy. Thank you so much for your presence.